Well, good morning, everybody. This is take two. We had some technical difficulties just a second ago, so you're going to have to wait for a few minutes here. And if you're watching this in replay, and give us a chance to have everybody who was on the old stream find the new stream, and we'll start over. I was just getting started with our Skagit Gneiss Napeequa Schist show. I'm getting more mature as the years go on, but this is still a drag to have this technology just completely fail in the middle of a show. So of course I don't have wireless on my laptop going at the moment. Give me a second, please. Susan says we're 5 by 5 on this second stream. We have more than 100 who have kind of found the new. Come on, you son of a gun. Uh-oh, Daddy's starting to get pissed. This is not going to be pretty. Keep it together, boy. Keep it together, boy. God. Well, good morning. Welcome to the backyard here in Ellensburg, Washington. Thank you for joining us this morning. Give me just a second, would you please? Okay. I appreciate your patience. Those that are just joining us or watching in replay, we had major technical difficulty. And of course, I'm still confused about what happened, but I think I'd like to start over, do a couple of quick thank yous with this stream, and then we will begin the program. I put a fair amount of time into this one. I want to deliver it. I don't want to wait 5 more days before I give it. So I'm hoping that somehow we can get everybody from the old stream onto this stream. This is the one that will remain. We have more than 300. Wonderful. Let's just keep our fingers crossed. Okay, we're starting over. I'll be quick if you were with us before. First of all, am I 5 by 5? I am? Good, wonderful. 2 quick thank yous. Thank you to Jeff at Vindman's Bakery in downtown Ellensburg, Washington for custom making a fruitcake, which I've been using. I've been using the concept of a fruitcake to talk about the exotic terrain basement. Jeff and son Sam and hard worker Nick down at Vindman's Bakery, thank you so much for the delightful gift. I don't really want to cut it open this morning. Maybe I'll never cut it open. Maybe it'll stay this way for the next 50 years. But thank you very much for your generosity. And the geekus in Alabama, in Yay, Alabama, sent this portable table for me to use to set up props and papers for these outdoor live streams, if I ever do them again. Kidding. Okay. Okay. Thank you for joining us. We will begin our program right now. The Skagit Gneiss, the Napeequa Schist, and the Cascade River Schist. Are you ready? Let's do it. The Skagit Gneiss is given. Up until this point, I felt pretty confident after spending some time. But it's going to take me more the last 48 hours to really wrap my mind around all the tiny morsels, the juicy morsels that are inside of the Skagit Gneiss. But we have a new color. We have a new color of the Skagit Gneiss. That's saddle brown with the Patrick pencils. The Cascade River Schist, a peach puff, isn't that cute? And the Napeequa Schist, an apple green color. And that's an apple green color we've used before. The reason back to the apple green, which we may not even really talk about in detail, we'll be talking about in short order. Okay, 3 new exotic terranes. Those are the colors, let it be known. Shall we look at a map? Now this map isn't going to help us much, Mappy McMap, because we have to zoom way in to northern Washington to see the new colors today. That's the scale. Even though the Skagit Gneiss, which is saddle brown, is crossing over into BC just a little bit, even though that's a big terrain for the North Cascades, it still pales in comparison. It's just a cute little baby compared to Quinellia and Stachynia, for goodness sakes. And yet there's major lessons to be learned, I think, from the Skagit Gneiss. So we need that North Cascades map. And we're almost up to speed with what we did the first time around, take 1. So here is our map we've been working on. Many of these colors are familiar. Many of these terrains are familiar now. The Straight Creek Fault, of course, catches your eye. The Easton, the Chilliwack, the Nooksack, and here on the east side of the Straight Creek, more recently, the Ingalls Ophiolite, the Windy Pass Thrust, the Chewaucam Schist, the Nason Ridge Gneiss. And that's kind of what we did last time. Now today, here's our new colors. North of the White River Thrust Fault is some apple green. That is the Napeequa. And here's more of that same Napeequa on the other side of the Eniot Fault. So we're going to save the Eniot till next time, if you don't mind. But that's obviously a major fault that abruptly stops at the Straight Creek. And then once we get north of there, we're into the Peach Fuzz or Peach Puff or whatever it was called, the Cascade River Schist. And then here's the bad boy, the Skagit Gneiss. Once we get up to the Ross Lake Fault Zone, we abruptly get out of the crystalline core, we abruptly get out of the Skagit Gneiss, and we're into stuff that's coming a week from today. So as I said in the last live stream, just kind of setting the table for this, up until this show, this is show R in our alphabet A to Z. I've made it this far feeling pretty good about what we're doing, and this is the first show where I feel like I don't have it. There's so much to learn, and I think that's in part because there are open questions about the Skagit Gneiss. Even though there's been some done on the Skagit Gneiss, there are still some open questions. More past shows. And maybe even with the Cascade River Schist as well. Okay? So that's kind of the layout. What is Act 1? And what does that mean? Team, what does that mean? Team, what does that mean? I'm part of a team. I'm probably a bench warmer, really, on the dream team. But the dream team are these three guys. And I've mentioned them in live streams, but today is the show to learn a little bit more about these geologists, because these guys will be with these units for the next few summers. We'll be writing up some brand new, exciting new scientific papers focused on the Skagit Gneiss, the Napeequa, some plutons, etc. So they're probably embarrassed if I call them a dream team, but I think I'll do that because these are both, all three of them, absolute top geologists. Bob spent more than 40 years mapping in the North Cascades. Stacia has directed a number of her recent graduate students exclusively or primarily on the Skagit Gneiss, and another gneiss nearby that we'll talk about next time. And Mike Eddy's the new kid on the block, but he's already cranked out some amazing scientific papers on the Yellowstone hotspot, potentially tied to Silesia and the impact of Silesia. That's coming down the road. So we'll revisit Mike. But these are the schools these folks are teaching at. They are all geology professors. They have grad students that they are supervising. And again, I hope you're willing to indulge me here. I do want to talk about them because it will, I think, give us some context for why this is a particularly important topic for me, because I'm part of the team, a minor part. I'm kind of video boy. I'm going to be spending time with them with these units up in the mountains over the next few summers. I'm doing this live stream series to teach myself some stuff. And of course they're going here because this is complicated. I emailed Mike, the leader of the team, a week and a half ago, and I said, I saw the proposal, the NSF proposal, and I have a general idea of what you guys are up to, but it would be helpful if I knew some specific places or specific rock units that you will be looking at least in the next couple of summers, so that I know when I should sink my teeth into some new stuff. So here's an email from Mike. I'll just give you portions. Nick, very much looking forward to getting this project going next summer. As for target areas, we will be focused on the late Cretaceous through Eocene history of the areas east of the Straight Creek Fault. Good, that's today. Major plutons, remember a pluton is a big blob of magma coming up from below, invading the terranes from below. Major plutons included in these suites are Cretaceous plutons, the Eniot pluton, the Cardinal Peak pluton, the Oval Peak pluton, and some younger plutons, Eocene age, the Golden Horn pluton, the Cooper Mountain pluton. I'm adding pluton each time. The Railroad Creek pluton and the Duncan Hill pluton. Hardcore fans know some of those plutons. We will be thinking about the timing of emplacement of those plutons along with exhumation, I'll explain today, of the Skagit Gneiss complex, and motion on some of the major faults in the area. So the Skagit Gneiss and the Ross Lake Fault Zone are likely key areas for this aspect of study. Honestly, we don't have our act together yet for the actual logistics of next summer's fieldwork, if there is fieldwork with the virus thing. Stacia Gordon will be likely in history, again I'll explain. Bob Miller will be likely focused on the Ross Lake Fault Zone's movement history, and I, Mike, will be sampling the plutons to generate a high-resolution record of magmatism through these periods. All right, so these are the spots. If you know Washington geography, the town of Wenatchee, the town of Chelan, here's the Straight Creek. And so we're in this high country. I know I've never really been up hiking in that country at all. I'm excited just to get up there on the trails or at least some access roads and then hiking a little bit. And yes, Washington 20 comes through here as well, and we'll read a little bit of the Roadside Geology of Washington book with Daryl and Marley in just a second. I'm going to give you more. This is the show to do it. Here's Mike from his website. Just you can Google Mike Eddy, Michael Eddy, and you'll find his website and learn all about his research lab that he's building, his geochronology lab that he's building in Purdue. Here's Stacia, mid-career person, University of Nevada, Reno. She has a personal home kind of website, and then she's got another website devoted to her North Cascades work, so I'm sure you'll be able to find those, or somebody can link down below. And Bob Miller, who we talked about last time, San Jose State. This is from the San Jose State Geology Instagram page. I couldn't find many other good photos of Bob. But this is Bob, something like his 44th summer in a row that he's come up to work in the North Cascades. So obviously there's a lot to learn from him. And yet he's still learning new things to add to it. Back to Stacia, one of her star grad students, Kirsten Sauer, has cranked out, I don't know, I've lost track, 3 or 4 spectacular scientific papers on both the Skagit Gneiss and the Swakane biotite gneiss that we'll talk about next time. But she was under the tutelage of Stacia at Reno, and maybe Kirsten's still there. And this is all from Stacia's website, Stacia Gordon's website. She's got some new grad students, Lizzie Langdon Lasagna, I believe. Lizzie Lasagna reminds me of a kid that we used to hang out with in Sweden when our kids were young, Nicky Noodle. So Lizzie Lasagna, looking forward to meeting her. I assume she'll be part of this approach and this grant the next couple of summers. And Anne Hunt Hansen just finished her master's under Stacia's work, and she will be cranking out some publications as well. So there's a lot going on with these guys, and all you have to do is go to Stacia's website to get a sense of the beauty of these rocks. If you thought the Napeequa Schist and the Nason Ridge Gneiss last time were beautiful, there's more stunning photographs from Backcountry Gary and another Gary, and we've got a video field report from Tim, who will get us up here as well. So this is one of those places that has challenges intellectually galore, but of course also physical challenges, and just you feel completely alive. You feel completely alive when you're up in those places, working hard, like I know. One more from the team. You remember last show I asked Bob Miller and Scott Patterson to give a little background on why they are actually even working in the North Cascades, and I asked Stacia for the same thing. She gave me a couple paragraphs. This is Stacia Gordon talking from Reno. Never met her yet. Nick, as you've probably noticed, in each person's blurb, Bob Miller is mentioned, and he is to me the heart of North Cascades geology research. I think this summer may be Bob's 44th field season in the Cascades. I was introduced to the North Cascades during my PhD at the University of Minnesota. My advisor was Donna Whitney, who was another University of Washington alum with Bernard Evans, and she did her PhD in the North Cascades. And Daryl Cowan, who may be with us, you know, Daryl's got his fingerprints over all of this and connections with everybody, it seems, as well. Donna, Bob, and Sam Bowering at MIT had a grant together, and half of my PhD was funded by their grant. After I started at Reno, Bob and I decided to write a proposal to work on sedimentary incorporation into the arc. That's what I'm having trouble with, and we'll get to it. The Skagit Gneiss and some sedimentary incorporation, metacenter. We'll get to it. And then Mike is now part of the team as well, because Mike was at MIT and doing that high precision work. As Bob emphasized, the work in the North Cascades has been such a pleasure because it is absolutely beautiful country, and we get to go out, hike around, catch up on life, talk geology, work geology with colleagues and students that I consider to be really good people and good friends. Okay. So, getting back to the content, you recall that our first taste of the crystalline core was in the last show, and I emphasized to you that there's, in the crystalline core, very hard rocks, very high relief rocks. The mountains are jagged and beautiful, and the whole area is just completely shot through with these plutons, with these liquid blobs of magma coming up from below. And these dates that you can see, this is just one of many, many maps that exist in all these reports. These are ages and millions of years. And so it's many of these plutons that Mike is going to do some new work in. I don't really know what he can learn that these guys have not. I'll learn from him. And again, Tim from Bonnie Lake is going to be visiting a couple of these plutons for us in his video field report that's very well done. Here's that same map-ish, but using our colors. So do you recall there's Mount Stewart Pluton that invaded the Ingalls complex and the Napeequa, and I told you it even invaded the Nason Ridge Gneiss. And I don't think I hit this last time. I meant to. Last time I did this, and I tried to emphasize, and I think I did this, that the windy pass thrust, where the Ingalls ophiolite is thrust over the top of the Chewacam Schist and the Nason Ridge Gneiss, that all happened, and then the last thing to happen, and cutting across everything, is the Mount Stewart Pluton, 96 to 91 million years old. What didn't I hit hard? The Mount Stewart Pluton is a stitching pluton. I didn't use that phrase, but I wanted to. So we've flirted with this idea of a stitching pluton, but let me try to emphasize right now the significance of a stitching pluton. Many of you in previous shows asked, okay, so the terranes came in from different places. Why are they still together? And I kind of hemmed and hawed. I didn't have a great answer. I think I have a great answer here. It came from some of your answers in the live chats in past shows. I think one way to visualize why these terranes are still glued together is that since the terranes were brought in and assembled and we made the fruitcake, then we shoot the fruitcake with all this liquid from below, and we literally stitch the terranes together. And in some cases, those plutons have then been cut by strike slip faults and offset, but for the most part, like the Mount Stewart Pluton, it hasn't been offset. It hasn't been monkeyed with much at all since its emplacement 96 to 91 million years old. Okay, so stitching pluton, we're going to come back to that again today. Good morning. I also mentioned to you that Mount Stewart Pluton is at the southern tip of this absolutely mind-blowing belt of metamorphic rocks invaded by plutonic material. And we're going to have a full live stream sometime later in the alphabet to really dwell on why, or at least describe what are the ages of all these plutons. Is there a chemistry change through here? And then ultimately we might speculate on why all that magma was coming up at a certain place. I've also failed, just housekeeping now. Mike in Seattle sent a couple of beautiful photos, including this one. So here's the stitching pluton, Mount Stewart Pluton, granitic in nature, that is younger rock than the foreground here, which is the Ingalls ophiolite, which itself was thrust up on the windy pass thrust. So all this was here first, continuous, and then even though this is higher today, it's younger and made its way through. Okay, am I stalling? I don't know, kinda, maybe. Trying to get my heart rate down. Just before you think that these plutons are sitting there as these big bowls of jello or something, you can see how incredibly folded the plutons are. So it's not like it's been a quiet Sunday morning ever since 96 million years ago. So the plutons themselves have been screwed up. But of course, we're trying to get this all visualized the best we can. And by we, I mean me, damn it, I mean me. Okay, so I've talked about the team. I've tried to set the stage. And it's time to actually start looking carefully at the rocks. And then number 3 is where I'm going to have more questions and answers, but I'm going to throw out a bunch of rapid stuff that seems to work for me. And that seems to work with me is the wrong thing to say. Have you noticed sometimes I think about the next thing I'm doing, and so I finish a sentence that doesn't make any sense? You're very forgiving with that, by the way. Sometimes I misspeak on hard stuff. Sometimes I misspeak on easy stuff. But I'm always thinking, and you're very good about not jumping on that too much. As always, I'm using a bunch of resources to put this together. I'm using popular literature by this Tabor and Hagerud book from more than 10 years ago now. And they're showing us a peek at some of this material and how complicated it is in cross-section. And of course, there's gorgeous photographs of all these rock units. I promised to read a passage from the Marley and Darrow book at the appropriate time. Remember Kirsten Sauer, the star grad student of Statia. This is just one of many of her scientific papers on the Skagit. Transfer of meta-supracrustal rocks into the mid-crustal diff. Wish I could understand it better. Here's Stacia and Bob. Now that you know, 2 of the 3 members of the dream team, a 2009 special paper, a 2009, I think this all coincided with the GSA meeting in Seattle. Sorry, in Portland. I just did it again. Thought about the next thing I was going to say. Just giving you a place you can go in case you really want to get into the gory details. I've already shared Field Guide 49 with you. There goes the sun. And here's Stacia putting a field guide together, a field trip essentially for the Seattle GSA meeting. And so with Act 3 here, it got to a point yesterday morning where I'm like, I just can't do this. I cannot learn this. I don't have the background. So I emailed both of these guys. And they both got back to me by email. So I'm going to read some of their email from last night to give you a sense of at least where I am, and maybe you can be too. I haven't used these, but we can also go to Routes and Rocks by Roland Tabor. We could even go to Fred Becky and his climbing routes that also have some geology in them. So there's no shortage of literature, both old and new. But what am I trying to do? I'm trying to make this work for a general audience. And I'm trying to make it work for my head. So that a map like this Ralph, 2009. Can you see why I've avoided this area for 30 years? And you're like, well, no, wouldn't this be an exciting place? Like, let me at it, let me figure it out. Well, let's just say there were more obvious, easier things to learn in the first 30 years of being here. Columbia River basalts, Ice Age floods, things like that. But now I have motivation to get up here. All right. Had that idea about 20 minutes before we started. So we've been doing our strat columns. And here they are laid out side by side. So when we got down to Washington after building British Columbia, we started plotting these strat columns. Do you recall? San Juan Islands. And look at how old some of this material was. This is stuff we decided that came from a long way away, tied to the Alexander story coming through the Arctic. And then we got over to the Western Cascades. Sun's back out. Hang on. I'm going to have to shower and nap after this one, maybe at the same time. Then we got into the western foothills around Mount Baker volcano, for instance. We saw the Chilliwack. We tried to correlate a little bit of this. Chilliwack, is that the same stuff as Turtleback? Maybe Ned Brown thinks so. Darrell, I think so. Bell Pass Melange, still a bit of a question mark with the Twin Sisters Dunite. You've never been? Right, haven't been. Incorporated into this mess. And then really we were speculating but not sure how to correlate these guys. Noticeably younger rock. Some Ocean Island stories there. Then we ran into the Straight Creek Fault and realized, okay, now if we cross the Straight Creek Fault and get into eastern the eastern side of the Straight Creek. There's the Ingalls from a couple shows ago. Well, suddenly we don't have anything down here. We don't have any correlations with some of these oldest rocks. I don't know, is there anything east of the Straight Creek Fault that's going to be old like this that we can correlate? Or do we even want to correlate? Is that a mistake at this stage? Let's leave that one open. But we're still in Friday's show, the show we did 48 hours ago with the Chewacum Schist and the Nason Ridge Gneiss, and realized that it was considerably younger than some of our stories we talked about before. Well, here we are. I got questions. I've got a weird like double box thing going on. What's that about? Well, first of all, let me just give you the headlines. Rock-wise, the things we want to focus on with the Napeequa, the Napeequa Schist, it's definitely a schist, but there's some amphibolite in there as well. In some places, major amounts of amphibolite. That's a new word for us. Amphibolite is meta-ocean floor, meta-basalt. You take a basalt and you cook it, it becomes an amphibolite. So we'll see amphibolite a fair amount in the coming shows. Mostly schist, but amphibolite. Let's pause. I drew out some concepts for this. And as I did this, I realized, I don't know if this is the way to do it. Like after I got finished, I didn't want to write it again. I think we want to visualize these as their protoliths, in other words, the original rocks. This is the age range for the original scene before the metamorphism, before the change. Everything's metamorphic here. These three new terrains are essentially all metamorphic rocks. And of course, metamorphic rocks we know are rocks that used to be something else. They used to be sedimentary rock, they used to be granitic rocks, plutons. You take anything and you can metamorphose it and change it into a new metamorphic form. So, I don't know, I might redo this by next weekend and have these be the original rocks instead of writing down these metamorphic rocks. I think we're going to get the metamorphic rocks up here is my point. But that's a little bit of what I'm struggling with. So first things first, can I give you a couple of pictures for what you want to visualize for the original scene for the Napeequa Schist, which has not always been a schist. In other words, what did it look like originally before the Napeequa became a schist? Clipboards by Dave. So I've only been on one geologic field trip up to this area, and led by Chris Mattinson, Green Rocks Chris, who was here last weekend. So this is Wendy Borson and a bunch of grad students who are looking at the Napeequa. So this exposure of the Napeequa Schist, you go to Eniat, Washington, right along the Columbia, and then you head up a road heading to the northwest, and you eventually get away from the Columbia far enough to get some exposure of this Napeequa Schist. Again, there's beautiful photos coming from Gary and another Gary, but this is mine. Not nearly as artistic. And no yellow labels. I got to slow my mouth down. I'm amped, I'm jazzed, I'm off my game again because of this frickin' technology. I can't believe it. Can't believe it. Why are there so many major surprises with this frickin' wireless thing? Okay. Got it out of my system, thank you. Just in case you're curious, I finally powered the whole phone down, powered it back up. For some reason, I don't remember to do that right away, because it feels like a last resort. Relax, Nick, we're with you. Thank you, Rainey. Okay, thank you. So remember my opening statement. I'm less confident than usual. So the best I can tell, the original rocks of the Napeequa were sediments sitting in the deep ocean floor. This sounds familiar, doesn't it? We just did this last show with the Chewacum. And I said perlite. I misspoke last time. I meant pelitic. So we have deep ocean siliceous sediment, an ooze on the ocean floor that's eventually going to become deep water chert. And by God, we got another one of these ophiolites originally, like the Ingalls, but it no longer is an ophiolite because of this metamorphic scene. So this is just for starters. This is just for starters. This is just down here at the earliest days, and I think this is a Triassic story. Again, I'm going from this paper to that roadside book to that, and just trying to find a common message that I can use. So I'm cobbling together what I can from these various sources. But again, here's what I think I want to, I'll eventually change this. I don't want this to say schist in amphibolite down here. I think it's the original, which is what? Chert and ophiolite. And then I think I'm just going to ask, and Daryl might be with us and others, are we waiting until way up here? Are we waiting until 100 million years-ish to create the metamorphic activity? I don't think we have an accretion date nailed down for any of these guys. If they truly are all Triassic protoliths, I'm just not sure we have the accretion date, and therefore I'm not really sure we have the first age of metamorphism. Remember last time with the Chewacum we had what, 3 different metamorphic events with the same unit. So I don't have a sense of that. But something major happened 100 million years ago, and I'm going to get to that in just a second. Okay, so original Napeequa looks like this. And then here's my attempt to try to get us to the Napeequa today. If you're out banging on rocks, or you're out hiking with Backcountry Gary back in the 70s with the good-looking legs, sorry Gary, it's dominantly schist, and that schist was the chert originally. So you take the deep water sediment, you heat it up, you cook it, you pressurize it, it becomes the dominant schist of the Napeequa. But as many of the geologists that helped me for this show said, the Napeequa is like a dog's breakfast. It's got a little bit of everything. It truly is a complex. It's another accretionary wedge type thing. So I did not show you that concept here, but I did show you that concept here. I drew an accretionary wedge last time as well. Now this is apple green. Apple green's pretty damn close to grello, Patrick. I chose that on purpose. Some, I don't want to get too far into this, but some are wondering if we can correlate the Napeequa with the Cache Creek. Now the Cache Creek had Tethyan fossils, and I think Daryl points out there are no known Tethyan fossils in the Napeequa. But as far as the Bell Pass melange and this accretionary wedge and a few other complicated zones, possibly all the same story that they're being told, but I don't want to hit that too hard because I'm really not sure. Again, the amphibolite is that former basalt ocean floor, and then you throw in some marble, which probably was some limestone in an oceanic setting at some point, and there's even some ultramafics, which you recall from Chris Mattinson visit, was also kind of part of this ocean floor mantle story. Okay, we'll see a few photos in addition to my photo of the Napeequa, but let me remind you on the map where the Napeequa is located. I can show you this side. And so we were just looking at the Napeequa, which is on both sides of the Eniat Fault. So at Marble Mount, the town on Washington 20, and you cross the Straight Creek Fault, you're getting into some Napeequa straight away. And then the road continues and gets into some Skagit. You know, I'm going to wait. Really want to read that passage from the Roadside book. Here you'll notice that the Napeequa is thrust over the Chewacum. just like the Ingalls was thrust over the Chewaucan, but they're coming from different sides. The black teeth are on the upper plate. Okay, let's keep it moving along. Let's go to another schist with a different story. That's why they're not all called the same unit. There's two schist units, but there's different colors because there's different stories, different terrain. I haven't gotten to the Skagit Gneiss yet, which is the mind blower for me. I'm looking at my watch, but why? Why? I'm glad, you got 750 people here. I'm glad you found the new stream, and I hope that you're enjoying this. Well, there's a weird symmetry here. Is this me just trying to be tidy, or is there really kind of some correlations here between these three? Not sure. But same caveats about this. I think I want the original look, which I'm going to show you in a sketch. And then I'm wondering if we don't get the schist and the granitic, the kind of meta-granitic material, until we get younger than 100. But let's go ahead and look at the Cascade River Schist and at least get a sense of how different the story it is. From what I can tell, this is an ocean island arc story. And not only do we have Cascade River, which ultimately is schist, but originally is shales and maybe some turbidites and some sandstones that are being deposited on the flanks. Remember, we've done this a couple times. Do you have a good memory? Further west, we had pictures like this. And back then with those pictures, I would say, what is this? Is this one of the green beans? Is this Tectonic? Is this Quinellia? I have the same question today. We only have so many island arcs that were created in the ocean and were added to the Pacific Northwest in this age window. But as far as I can tell, we don't have a way to correlate yet. The wrinkle here is that there are some things called the Marble Mount plutons, which are in this window of age. So we're back in the Triassic. And originally this kind of granitic material, granodiorite is just a slightly dark colored granite. This magma chamber that fed the cone is now all metamorphic. All this stuff is metamorphic now. It's mostly schists and gneisses. Now I just had a flash. When we filmed on the San Juan Islands with Daryl Cowan up on the top of Mount Erie, we were talking about this in Fidalgo land. It's tempting to try to connect some dots, but the researchers aren't doing it necessarily, so I don't know if we should either. That's all I have for the Cascade River, except for a few photos from Gary. But our peach here is north of the Napeequa and south of the Skagit Gneiss, and you'll see it squeezed into all sorts of interesting nooks and crannies. Now, we're finally to the main event, and the one that was on my brain as soon as I woke up early this morning. And it's the Skagit Gneiss. Now, let me finish the thought. So just like these other two boxes, I can't even remember, did I do it? I at least have a concept for the original look, but this is buried in the literature. There's only a couple places I saw a Triassic protolith for the Chewaucan, and I'll just jump to it. One of the mind blowers for me, and the reason I'm so damn confused about the Skagit Gneiss, is that Stacia and Kirsten, her student, and others are picking through the Skagit Gneiss today, and they're finding grains of zircon that are, late Precambrian, and there's all sorts of, they don't make sense to me, the kernels of detail within the Skagit Gneiss, as well as some other things I'm about to get into. But I tried my best to kind of do the same thing I did with these two other guys, that we have some sort of former look before the metamorphic story, and then we have the metamorphism much, much later. So do I have anything? I do, and it's almost like a broken record. Colored saddle brown, I might add. No big deal. Same basic ages. Am I making this up? Possibly. I think the same general age window, Triassic, the same general story that we had with the Napeequa. We maybe don't have an oceanic complex here eventually, but for starters, as I pecked through all these rock descriptions and various sources of the Skagit, if I could read through all the fine print, I think I found some of this protolith material, which is a similar story to us. And I keep saying that because maybe at some point, maybe now, maybe the dream team will be able to convincingly show how some of the terrains up in British Columbia can be swung through the North Cascades, but we're not there. Okay, we're finally to the, deep breath. Can I do this in a coherent way? I will try. So to me, as I understand it currently, there's a 3-act play just with the Skagit Gneiss. I hope this is real. I'm not entirely confident it is, but let's just say I'm giving you something real. That there's a Triassic beginning to the story of the Skagit Gneiss. And one of the reasons I think there has to be some of this old rock in the Skagit originally is because the plutons that are going to come in and invade everything, doesn't there have to be something there in the Skagit before we bring the plutons in? Because most of the Skagit Gneiss has a young story. That's really the headline. Most of the Skagit Gneiss is creeping into days younger than the extinction of the dinosaurs. We're still making Skagit Gneiss at 60 million years ago. That's a shock to me. Up until this weekend, without thinking about a whole lot, I assumed that there was a protolith for the Skagit Gneiss back in the Mesozoic, early Mesozoic, mid to Mesozoic, Triassic. And then we create metamorphic rocks. And I assume that everything was built, everything was metamorphic by 100 million years ago or shortly after. And then here comes this crazy invasion of all these plutons from below, invading what? I thought all that metamorphic story of the Skagit would be there for the plutons to come through, just like the Chewachem Schist was a Chewachem Schist. Remember, the Ingalls was thrusting over the Chewachem Schist. Everything was metamorphic that needed to be metamorphic, and then Stewart came up through 93 million years ago. Daddy's excited. But here, the famous gneisses, the hallmark gneisses of the Skagit Gneiss exotic terrain, orthogneisses and banded gneisses. There's one photo in particular from Gary that I can't believe the photo. It's perfect and it's exciting. It just leaps off the page to me. I think I might buy that one from him and put another Gary photo on my wall. That photo is so amazing. So these gneisses are beautiful. I'm giving you the difference, and this is from many sources. I didn't really know the difference till now. Orthogneisses are pretty much just taking those granitic blobs that invaded here and then metamorphosing them, creating an orthogneiss. So you have a gneiss. Do you have a mental picture of a gneiss? I showed you this as just kind of a generic gneiss from last time from the Nason Ridge, even though it's not, but I just grabbed one from the 101 lab. Foliated, black and white minerals, and oftentimes you can get some segregation of the black and white minerals and create these bands, these kind of zebra stripe looking things. So this is a gneiss. Let me give you a more sexy one. This one, not so much. But again, you can see there's organization of these minerals. I'm not going to flip you around. There's not enough good sun. Not from the Skagit either, I don't think. I think just from the Appalachians, but been cut by a rock saw, obviously. But this is the gneiss look that we're talking about, the banded gneiss. So again, if we're talking about orthogneises and banded gneisses, the orthogneises are interpreted as pretty much 100% igneous stuff, plutonic igneous stuff that's been changed. And the banded gneisses then have kind of these light and dark bands. And as I understand it, generally, the dark bands are that former ocean sediment. So it's like a schist type mineralogy. And then the light bands are more the granitic stuff. Okay, well that's doable, right? Is now the time? No, it's not. If I stop there, and that's all I have to say about the Skagit Gneiss, I think maybe I feel pretty good. And we can add one more concept that's more challenging and interesting, I think, but also doable for this old noggin. And I hinted at this last time. By looking at the minerals, the metamorphic minerals in these gneisses, in the Skagit Gneiss unit, there is a very clear picture of this whole portion of the Skagit Gneiss drastically going deep into the earth. Like we're going to thicken the crust dramatically. I forget the number, 55-kilometer thickness of the crust. Like something happens 100 million years ago. And shortly after 100 million years ago, these plutons are invading and thickening the crust. Now, are they causing the thickening? Some say yes, most say no. But the point is, we're getting this material and we're going to create these gneisses at 20 miles depth. I don't have a good analogy for you yet, but we had a simple ocean scene. We're creating metamorphic rock on land, but the metamorphism primarily is happening in the dark 20 miles below the surface for a long time. And then equally interesting, but not really part of this series because it's so damn young, exhumation is saying, look, we're going to take all this beautiful gneiss of the Skagit. It's still deeper than 20 miles below the surface of Washington at 50 million years ago, but by 45 million years ago, it's all at the surface. So this up of the geologic elevator will come back again when talking about at least the Chelan megmatite next Friday, but maybe even the Swakane, I'm not really sure. But exhumation is the concept that we're bringing all this stuff back to the surface, and so we're eroding incredible amounts of material, overburden that was sitting there on top of this banded and ortho gneiss of the Skagit. And then the obvious question is, what happened to all that sawdust? What happened to all that material that was eroded away as we have the geologic elevator come back up? So I'm working on those concepts. We're still not to the main problem for my brain, however. This is all just within the Skagit Gneiss. Can you see why this is worth some time and some energy and more research by the dream team? So going down, geologic elevator going down, make all these rocks down there, 20 miles back up in a very short amount of time, get it to the surface where it basically is today. Yep, okay. So before I read the passage from Marley and Darren's book, before we go in the Cozy Fort and look at some photos and a video report, I have one last thing I'm doing with the Skagit Gneiss, and it's the hardest part of the whole thing. Stacia and her student Kirsten have been doing all sorts of geochemical work with zircon grains, work with a bunch of stuff in the Skagit I don't even really understand, obviously. But the concept is this. Stacia and Kirsten didn't come up with the idea. It's been around for a while. But when we're making, this is not a magma system now, this is where we're making the gneiss of the Skagit Gneiss. Remember, we're down at the bottom of the elevator now, 20 miles below the surface. And the temperatures or pressures are appropriate to make the banded and the orthogneises. In the middle of that scene, apparently the temperatures are too low. And there are certain signatures in these gneisses that are too weird to just be a normal scene of taking the original protolith and making it into a gneiss. In case you're still with me, in green is sediment. Large volumes of sediment. Sediment riding on the ocean floor. Sediment in what's called a four-arc basin, which is a basin filled with sand and mud and clays that are before a volcanic arc. Even sediment in a back arc. So there's just basically tons of sediment nearby. This is the part I can't picture. That is being incorporated into this gneiss-making factory. Like this is, why not, I'll say it. This is like a campfire, and you keep tossing a bunch of, stop, that doesn't work. That's going to get us into magmas. Many geologists, including the dream team that I'm working with now, have major stories of sediment being incorporated into this metamorphic Skagit scene. And I cannot quite picture how that works, when it works, even really why it's necessary. And when Stacia and Bob and Chris Mattinson see this, they'll go, I sent you the emails. Why didn't, I think I was pretty clear, wasn't I? Well, I'm a slow learner. So I want to read a little bit of their replies to just at least flesh out the idea about sediment, meta-sediment incorporation into the Skagit and why that has to be part of the story. And then it was probably in Mexico. What a mess. Oh my God, what a mess. So we're to the part that's open-ended where I just can't bring these things together. These are just things that catch my eye that are damn interesting. This is Friday, no plutons coming through it at all. Here's what? Today's Napeequa, last time's Chewacum. Look at the invasion of all the plutons at certain depths in the past. And here's our buddy the Ingalls and the Windy Pass Thrust. Here's Daryl. Is Daryl with us? Daryl back in the 1980s. Now this is long before Stacia and Kirsten Sauer are working on this sediment incorporation. But he's trying to think about how we can get major amounts of sediment going down a subduction zone from the ocean floor, accumulate an accretionary wedge, Forearc Basin, Backarc Basin. How do you get that stuff in to the depths of the arc? If you like the eastward subduction model, here's one diagram to help us see. Sure, we're going to subduct an ocean plate, but the sediment riding on the ocean plate is going to get scraped off, but not all of it's going to get scraped off. A bunch of the sediment is going to go down the tubes and somehow get into the guts of this mid to deep crustal level. So I sent 3 questions to Stacia and Bob, and Daryl got involved there at some point too. I'll do this quickly. To Stacia and Bob primarily. This is me yesterday morning. In 2009, in your papers, you guys, you're talking about regional crustal thickening and underthrusting of some sort of cool outboard terrain to explain the low temperatures that you see in the mid to deep crustal volcanic arc of the Skagit. 10 years later, now you're kind of talking about a meta-sedimentary rocks shoved into the deep levels or the mid-levels of the crust, producing significant mechanical and geochemical consequences. My question is, are those both the same concept, or did you abandon the outboard terrain idea and substitute the meta-sedimentary rocks idea? Here's Stacia. They're a little different. The outboard terrain is referring to terrain accretion of the insular, so accretion of a relatively large body along the paleomargin of western North America. The meta-sediments are much smaller bodies and are interpreted to represent sediments likely derived from the Forearc Basin adjacent to the volcanic arc that used to exist in the North Cascades. We interpret that parts of the Forearc Basin were underthrusted into the arc. Bob was replying at the same time, basically, so he saw Stacia's comments before he hit send on his. He'd say, I'd say it's something in between. The regional crustal thickening we talked about largely applied to the mid-Cretaceous, 100 to 85 million years ago, and focused on our work in the Wenatchee Block, where Scott Patterson, Jenny Matzell, and I had done most of our work at the time. It's also simpler in the south, because it doesn't have the later magmatism and metamorphism of the Chelan Block. We envisioned underthrusting of the Napeequa. So there's a little difference between Bob and Stacia. And unknown rocks below the Napeequa. A few years ago, Kristen Sauer did the detailed dating. She largely focused on the Swakane and the Skagit, which were underthrust and metamorphosed between 74 and 65 during another round of pluton flare-ups. I'm not going to read all this, but I basically just kind of basically asked these guys, is this a thing, like sediment going down a subduction zone? I didn't even really realize, aren't we scraping all the sediment off in a trench? Why is some of the sediment going all the way down? I like Stacia's answer the best. She says, I think of it as a bulldozer pushing the sediment, and it is building up in the accretionary wedge. But that bulldozer blade isn't cutting all the way down to the base of the sediment, and some of it's slipping below the blade. I'll finish with Stacia's comment. Some of the meta-sedimentary rocks in the Skagit Gneiss are not related to the rocks that were present and represented the crust when the arc magmatism began. We know this from their detrital zircon data and geochemistry. Thus, the protolith to these meta-sedimentary rocks had to have been incorporated into the Skagit Gneiss area. Okay, so all I can say is to be continued, but I'm going to finish our session out here with this. If we're truly going to the big picture, this is just a tiny little figure in the Hagerud Tabor North Cascades book, and it always caught my eye. Because they're saying, hey, look, we've got thrust stacks, we've got pizza boxes, we've got these terrains that are relatively thin and they're thrust up on top of one another, and it's definitely a compressional story. And those scraps that are thrusted onto each other in the San Juans in the western Cascades foothills. Yeah, we can even see some of those thrust stacks in the crystalline core. Those mostly have an oceanic story, and their figure says the timing of this is all about 100 million years ago, when you have two tectonic plates, or North America colliding with something, and you're crunching and you're squeezing and you are shearing and you are abducting or taking some of this ocean stuff and getting it up onto North America as opposed to going down the subduction zone. What is this main event? And is the main event from a westward subduction story? Or is it an eastward subduction story? So of course I'm calling back to Karn and Mitch and the stationary insular. Is this the insular that's stationed out in the Pacific, and here's North America coming at it? And all of this thrusting and all of this magmatic flare-up business starting 100 million years ago, is that all in response to us plowing through the insular? I'm not sure where the Dream Team stands on Karn and Mitch's work. They may be violently opposed to it. Most of their figures are looking at eastward subduction and somehow getting all this sediment into the mid-level of the crust that needs to happen for the Skagit. But I wonder. Okay. Did I say I was going to do something else out here? I don't think I did I? Oh yeah, I was going to read a little passage from Roadside. So many of you purchased this as a companion to our series, and I thought maybe at some point I would use, like, refer to individual pages and we'd all look at it together. I'm not really doing that because I'm more of a freelancer than I thought I would be. Colors are wrong for us, but again, Marley's map showing different shades of purple for the crystalline core and Mount Baker on the other side of the Straight Creek Fault. But just in case you've never used a roadside geology book or an excellent one like this, I think I do want to take just a few moments and show you the power of a well-written book with beautiful maps as well. So here's Marley, who makes these amazing maps, and here she's taking us on Washington 20 through Concrete. These are towns in northern Washington: Rockport, Marble Mount. We're crossing the Straight Creek Fault right here. Colors are wrong for us, but she's getting us into the Skagit Gorge. She's giving us all sorts of details at neighboring landmarks. And yes, you're driving right through this very complicated Skagit Gneiss. So she has a passage that I assume she wrote with Darrell, Burlington to Marble Mount, but that's on the wrong side of the Straight Creek Fault for us. So I would like to, please, if you wouldn't mind, read to you just a few little paragraphs to apply some of this concept of our three new terrains today to a simple drive that you and your family can drive the next time you can get up on that road without a bunch of snow and without a bunch of virus. At the east edge of Marble Mount, you cross the Straight Creek Fault at the Skagit River and pass into the crystalline core domain, where the hardest rocks of the Cascade form its most rugged landscapes. Intrusive rocks, mostly granitic in composition, formed in the roots of ancient volcanoes, similar to today's Cascade volcanoes, and younger intrusive rocks cut across the older ones. Metamorphism occurred from late Cretaceous to Eocene. Okay, I think that just answered my question. The metamorphism did start as early as the late Cretaceous. Oh no, I was saying that. Washington State Route 20 follows the Straight Creek Fault northward from Marble Mount over forest-covered river deposits. You gain some nice views of the peaks in the western domain made of schucks and green schist. You gain some nice views of the peaks in the western domain made of schucks and green schist. Halfway between milepost 109 and 110, you encounter outcrops of a Triassic age metamorphosed granitic rock called the Marble Mount metaquartz diorite. That was in the Cascade River Schist, correct? A good pullout lies just east of the outcrop at milepost 110. Look for a metamorphic layering, a foliation, defined by green and white micas in a parallel arrangement. In some places you can see the foliations folded into tiny corrugations. Just east of the park boundary, North Cascades National Park, you cross a fault and enter the Cascade River Schist. Many good outcrops appear on the north side of the highway. The schist originated as shale that was deposited on the quartz diorite in a volcanic arc prior to metamorphism. Skipping ahead, Washington 20 follows the Skagit River Gorge as far as Ross Dam Trailhead at milepost 133. Along the way, it passes an uncountable number of awesome exposures of the Skagit Gneiss complex, the main rock unit of the crystalline core. The complex consists of two parts: light-colored ortho-gneiss, formed by metamorphism of intrusive igneous rocks, and darker-colored banded gneiss, formed by metamorphism of both intrusive and sedimentary rock. Some of the original sedimentary rock was deposited as far back as the Triassic. I took that and ran with it. Some of the original sedimentary rock was Donna Whitney, a metamorphic petrologist at the University of Minnesota, determined that the gneiss is formed at temperatures greater than 700 degrees centigrade and at depths of 20 miles in the crust. Between Nowalem and the milepost 125, outcrops consist of ortho-gneiss. A good place to stop is Gorge Creek, halfway between milepost 123 and 124, etc. Doesn't this make you want to take that drive? Doesn't it make you want to get out there and see this stuff? It does me. Maybe the photos will do it for you. Maybe the photos will do it for you. It's all right there, and it's not just along a busy state route, it's also up in the high mountains. The plutons are up there, the metamorphic rocks are up there, and Bijou is up there. Come on. No time for you. Time for the Cozy Fort. Thank you for paying attention. Thank you for trying to at least absorb some basics from our new terrains from today. 100 million years ago is the main event. What the hell happened? Sorry, Patrick. Time for dinner. Oh, baby. Cozy Fort by Steve. We still have almost 800. I'm so grateful to you. You come every time. You stick with it even if we're off the air for 20 minutes or whatever it was. I don't think the rest of the shows are going to be as difficult as this, but what do I know? If it's unclear to you, we will be making more and more correlations regionally, which is fun. So there'll be plenty more open questions and unsolved mysteries, but there'll also be a chance for us to go to distant places, from Alaska to Mexico. So we're not done being out of the country or out of the state. But we're not ready to go yet because we've got some stuff to do with the Skagit and the Chelan. That's next show. With the Swakane biotite gneiss and the Chelan, which is the next show. And also the Metau. Oh God, I am out of sorts. Daddy's out of sorts. All right. I'm muting us, and we'll do this relatively quickly. I don't think I gave Backcountry Gary the proper treatment. I'm not even sure I went full screen with his beautiful photos last time. So a couple of repeats from last show. Looking back at the stitching pluton of the Stewart pluton, stitching the Ingalls and the Chewacum schist together. That is Gary, back in the old days, he confirms. And we were looking at the Chewacum schist, which was originally ocean sediment. These are repeats from last show, more Chewacum schist. Still having trouble showing you the details of this photo. I really wanted to give this one a second try. The Napeequa Ridge Gneiss. Not today's topic, but that Napeequa Ridge Gneiss, my goodness, I want to be there right now. I mean, I like being here with you, but those mountains are calling, baby. Okay, to today. Does Gary have some more for us? Well, sure he does. First of all, he's looking backwards to the south to the last show. We haven't addressed the Leavenworth Fault at all. I'm not sure we will. There's a good example of a young graben with young sediments that are concealing more of our fruitcake. But to the right, you can see Stewart and the Chewacum. But now if we start heading towards the north, there are some friends. The Napeequa Schist, which has a deep ocean origin and has that crazy mixture of schist and amphibolite and other blocks of material. But the chert seems to be a major part. The meta chert seems to be a major signature. And to some geologists, the Napeequa Schist is a key unit in the North Cascades. If we can totally understand what the Napeequa is, we can maybe understand some neighboring terranes as well. Maybe. Come on. Gary sent this one twice to me because originally he had it labeled as a certain unit. And then he said, no, I just read that it's Napeequa. So Gary always thought it was Skagit, but now he looked very carefully at Roland Tabor's map and said that's Napeequa. Look at how chaotic the Napeequa. And the batholith is too young for us. Remember, the plutons are invading from below. Oh my God. We're still not to my favorite photo yet, but this is up there too. It's a rare treat for us to not only have a great photographer, but a guy who has spent decades in the backcountry professionally. He worked for the National Forest Service. I told you about Gary before. So in fact, he takes the time to label these with his yellow labels and plug them right into our descriptions today is a rare treat. Thank you again, Gary. Now this is a different Gary, ironically, who said, I got a few photos of the Skagit Gneiss if you want to use them. I'm like, sure, bring them, send them on. There's more of Gary Paul, Backcountry Gary, but this is just taking a break with Gary number 2. I forget where you're from, Gary, I'm sorry. Gary number 2. Road cut. And some greenstone, which I didn't realize was a major part of the Skagit, but maybe it is. Thank you, Gary number 2. Back to Gary number 1. And the yellow label photographs. I mean, I assume some of these are going back to the 70s and 80s perhaps. Maybe they're old slides that you digitized, Gary. But in the foreground, of course, we're finally to the Skagit and the ortho gneiss. That needs a sediment batch introduced into the scene. Beautiful photos here, but mostly of batholiths that are too young. The Chilliwack is post-fruitcake. But they're still amazing. Okay, you ready? So I've never really hiked from this Washington Route 20 at all. But I definitely want to head, and Gary likes this photo too apparently because he took the time to take the map, show us where Mount Triumph is, and show us the orientation of his camera as he took the photo. Ready? Oh my God. I can't get enough of that photograph for so many reasons. But to me, that's an award-winning photograph and appropriate for us today, because I think as we look at this together, we can see why the Skagit Gneiss continues to hold an amazing amount of detail. I got to move on, but that, my God. Same area, but maybe a different perspective, showing again the Skagit in Mount Triumph. Is that right? Yes. But also some Napeequa squeezed in there. Thank you, Gary. Hosamine's coming in a while. We finished in the Cozy Fort with, it's been a while since we've had a video field report, and Tim from Bonnie Lake sent this to me weeks ago, and I said I'm going to hold on to it until we're ready. So Tim, we are ready. I've got the volume cranked. I'll get my lapel mic out here, and this is 3 minutes long. Hope you enjoy it. And he's stopping at 2 plutons, one that cuts through the Skagit, so that's why I'm showing it today, but one that cuts through a terrain we haven't gotten to yet in the Methow. Full screen. This Tim deserves full screen. Tim from Bonnie Lake.
2-minute geology. 2-minute geology. Well, welcome to the North Cascades. My name is Tim Kirk, and I'm an amateur photographer, nature lover, YouTube maker, etc. But I've been a long-time fan, watcher, supporter of Nick Zentner at Central Washington University. I am an amateur but avid lover of geology, and so Nick has given us a challenge for 2-minute geology. I am right now in exotic terrain. This is the crystalline core of the North Cascades. And actually, this is the Black Creek batholith, a 90 million year old batholith of granite that accreted into the North Cascades as part of the North Cascades complex. It's a very well-defined granite with feldspar minerals, very polished and white rock. So I'm going to talk about this batholith, but I'm also in the neighborhood of another one that is actually quite a bit younger than this one. So we're right now standing in the Black Creek batholith, 90 million years old. But I'm going to head up trail, and I'm going to talk to you about a different view across Granite Creek, across the fault zone to a different and younger set of rocks. Well, I have made my way above Heather Pass, and I'm just off the trail here, and I've had to wait for a break in the people. There's literally hundreds of people going up and down the trail. Hey, everybody this weekend has the same idea. But let's look at Miller and Cowan's book, and page 159, it talks about the straightness of Granite Creek implies that it follows a fault zone.
Nice job, Tim.
And Washington 20 passes through the granite of the Golden Horn batholith. So we are now looking to the north, across Highway 20, across the fault zone at the Golden Horn batholith. And I said down below that we're in the crystalline core. Actually, I drove through the crystalline core to get here, but we're actually in the Methow domain. And if you reference in Roadside Geology on page 151, it does talk about the different accretions and batholiths of the North Cascades.
Yeah, Tim, nice job.
The difference is that this batholith, the Golden Horn, is actually intruded 48 million years ago. So there's a distinguishable difference of 42 million years between each side of Highway 20. We'll have to confirm with Professor Zentner, but I would say that is a typical lateral strike slip type of a fault. So I'm going to finish up this 2-minute geology challenge when I go up trail, and so we'll see you up there. So I'm just below the ridge line, and I'm going to end it here for this 2-minute geology challenge. I'd like to thank Nick for putting this challenge together. I hope you all enjoyed coming along to the exotic terrains of the North Cascades. I want to thank Nick for all that he does. We are all enjoying coming along on your exotic terrain journey this fall. So for all that you do, we all love you, and thank you very much.
Thank you, Tim. We have more of those video field reports coming from distant places, and we don't all have the skill that Tim has to put that together. Much appreciated. Let's try a few question and answers. I think you're still with us. Why not? I don't know how much battery I got left, but we'll just go for it here. Let me find us. And uppercase, please, for your questions. And I'll do my best to rattle through a bunch of these and at least take some notes for, if nothing else, your questions will be interesting to some of the researchers who will be seeing this show eventually, and they might just be curious what viewers of programs like this would want to know more about. And certainly I'm interested in your thoughts that way as well, as I am always. So, uppercase, please. London Liz, can you remind me what Karn and Mitch said about westward subduction? Sure, I can try. We're going to come back and revisit that for just a bit at some point. I won't take the time to draw it out, but let's see, you're looking, right. So this is North America, and it's been drifting west for the last 200 million years since the supercontinent of Pangaea broke apart. And the tectonic model that we've had for all of my career is that in addition to North America, a continent moving west, we've had a huge ocean plate called the Farallon Plate that's been subducting or diving beneath North America for the last 200 million years. So both plates are moving, but the continent is overriding the ocean plate down below. The model has always been, and I've taught this for a long, long time, that you can somehow get exotic terrains onto this ocean floor, or you can scrape off ocean sediment like we've done today, accretionary wedge, all that sort of thing. But the idea is you get the exotic terrains by having the Farallon Plate bring the ocean material to North America and scrape off the ocean stuff and add it on, whether it's an ocean island arc, or whether it's deep ocean sediment, or whether it's an oceanic seamount, or whether it's whatever. Karn and Mitch using old slabs of the ocean floor. In other words, we stress that the ocean floor doesn't melt. It doesn't just assimilate and change its state and go right back into the asthenosphere or the mantle and just disappear. Karn and Mitch, using geophysics and detailed fieldwork in Canada, have been able to find these old pieces of the ocean floor hanging in the lower mantle. And one of Karn's main points is that once you start subducting one of these ocean floors, it becomes a vertical drop and it starts folding on itself in the lower mantle. But once you establish that, the position of the trench and the subduction zone itself is not drifting. It becomes stationary because everything is tied to this folding ocean slab in the lower mantle. By using some math, some physics, and some other variables, you can go back in time then and figure out where North America was with respect to this stationary ocean island arc, the insular superterrane. The last part of this is, with Karn and Mitch's work, they say, how about we have North America getting closer and closer to the insular, but having the ocean crust in between my fist and my hand be connected to North America. And if we do that, if we bring the continent of North America closer and closer to the insular superterrane, we subduct westward. We don't really have the thing hanging like this. We have the thing hanging like this. So the insular is sitting out here as a baked potato. We have westward subduction, say Karn and Mitch. And as we do westward subduction to make the hanging slab, we bring North America closer and closer to the insular. 100 million years ago, roughly, is the main event when North America finally closes that ocean floor, crunches all that stuff in between, and my question is all of our thrust sheets getting caught between my elbow and my fist, getting between North America and a stationary insular superterrane? We'll keep revisiting it. Thank you, London Liz, for the suggestion to do that. I don't know if it worked for people. What mechanisms are at work to bring all that deep rock up to the surface? Great question. I don't know. I can't even share ideas. Great question. But the rock record says the stuff is deep at 50. It's at the surface at 45 million years ago. It rises 20 miles in There's 20 miles of uplift of the Skagit Gneiss in 5 million years. What's driving that? And where can we find the eroded remnants of the 20 miles of stuff above the Skagit? Sean, I just tried to explain what the big event was at 100 million years ago. I have no idea where Daryl, Chris, Andy, and the dream team are on that tectonic idea. Does the Skagit Gneiss show up in BC? Just a little bit, Rachel. Just a little bit, Rachel. Rachel, just a little bit. Where's my North Cascades map? I can't find it. There's no wind. Oh my God. This is a show to remember for a bunch of reasons. A couple more before we put this one out of its memory. What? Kent, it seems like the west to east subduction transition could create some confusing terrains. Is that what's happening here? Create some confusing terrains. Well, most of the terrains have an oceanic origin, some ocean floor, some ocean sediment, and it's here in the North Cascades. So I think the debate is the geometry of the plates and the timing of that. And then we throw in this geologic elevator going up and down. But we can't get away from the actual rocks that are there. And that's what I've been trying to do so far in this series. I don't want to arm geologists, former geology students know the phrase arm waving. Sometimes you go on field trips and they're just all waving their arms and talking about all these ideas. You get away from the rocks pretty quickly. The rocks are not changing. The rocks are the data that we have. All right, I'm to the low power mode on the camera, which means we're definitely quitting. One more and we're done. Zigsta, wouldn't subducting a spreading ridge give different products in the isotopic signatures? Yes, but I know of no one getting a spreading ridge near. Let's just say yes, that's a good idea, but I don't think any plate reconstructions I've seen has a spreading ridge offshore at that time window. Now that I say that, I think that's wrong. Good idea. Let me think about that some more. Ivana, we'll finish this out. Where does the Stachynia, Cache Creek, Quinellia story end? It seems like Washington rocks are more similar in some ways to Klamath Sierra, but Oregon Blue Mountains are closer to Canada. We'll finish with that. You clearly are patient people, so I know that you're not impatient about what we're doing. But to give you a little hint of where we're headed, and if you wanted to do a video report and you're in California or you're in Baja and you're somewhere else, you know, there's still time to make one if you want. I'm not pressuring you, but the next couple of weekends we will still be in the North Cascades, but that's it. I have a Pluton show in mind, and then I have a couple of shows in mind where we restore all of the strike-slip faults that we know exist, not just the Straight Creek, but other strike-slip faults. And so if we do that, we'll be getting Washington closer to some of these Northern California and Oregon rocks. And then we'll start talking about potential translation of stuff from Mexico or the Mojave Desert now up in the Spokane. That's a whole nother part, I should just say it, that's a whole nother part of the Spokane and the Skagit Gneiss. How much of the stuff we were talking about today is a Mexico story? Are you keeping track of the topics, discussions, data, interpretations, all coming from the Saddle, Brown, Skagit Gneiss and friends? That's why the Dream Team's heading there, not other places. A toast to you with Muffler Boy in the alley. I salute you for joining us today with a cold beverage. Ice cold. Here's to your health, your physical and your mental health, today, tomorrow, and beyond. Here's to the decades of field work done by very smart people who love doing this work, but also push through basic work to really excel with what they're doing. And I'm sharing work with you from people who excel at what they do. And especially these folks we were talking about today. You won't find anybody better than those folks. Here's to them. And as far as the technology and the Wi-Fi and everything else, I've learned as much as I can. I'm tricked out. I've got everything the way I can. So I'm just going to have to be philosophical. And when things just blorp and go away, I'll just deal with it because I don't know what else to do. And I'm not even really that interested in gathering more information and problem solving anymore. So we've had good luck lately. Today was a train wreck at the beginning, but we recovered and we still have 700 people. So here's to you for your patience, and we'll just hope for the best in the future. The next time I see you will be Friday afternoon at 2 o'clock. Will I be manipulating the fruitcake on Friday afternoon? Possibly. The fruitcake from Vinman's Bakery. Bijou's camera shy. There were 3 different times I tried to grab him. He's not interested in dealing with you. I think he wants to get in the house because he's cold. And I think I am too. So until Friday, I say thank you, I love you, and we'll see you on Friday with the Chelan Migmatite and the Spokane Biotite Gneiss. Got it. Goodbye. Goodbye.